This is a folding fin, canard stabilized rocket. I initiated this project as a proof of concept for a low-cost manpad system using 3D printed parts and consumer electronics. Here is a demonstration of the canards. And the procedure for loading the rocket. The total cost of the launcher and rocket system is approximately $96. While this prototype functions as a standalone platform, it was designed as a component within a larger experimental system. One direction I am exploring is integrating it with a distributed camera node tracking network. In this concept, multiple camera nodes triangulate the position of an airborne target and generate real-time XYZ coordinates. Those coordinates are transmitted to the launcher, which compares the target position with its own GPS and compass data to determine an optimal launch orientation. Once a rocket is launched, the camera nodes continue tracking both the rocket and the target simultaneously. Updated positional data is transmitted back to the launcher and then forwarded to the rocket, allowing the onboard flight computer to continuously calculate the relative position between itself and the target. The long-term goal is to explore how low-cost sensors, distributed tracking, and small autonomous vehicles can be combined into scalable systems built with accessible tools and rapid prototyping. Now, let's take a closer look at how the system is structured and how each of the major components work together. Once a rocket is inserted into the launcher and the umbilical cord is connected, the system is ready for initialization. Activating the primary system switch powers the launcher and creates a Wi-Fi network that connects to my computer. Through this interface, I can monitor key telemetry including system state, roll angle, roll rate, and servo response. The second switch arms the rocket by activating its internal battery. At that moment, the onboard IMU quickly measures the rocket current roll orientation relative to the ground. It compares this measurement with the calibrated orientation data and automatically adjusts the fin control logic and software. This allows the control surfaces to respond correctly regardless of the exact rotational position of the rocket inside the launch tube. Once armed and calibrated, the system is ready to fire. Holding the trigger for 1 second sends a command from the launcher to the rocket, which closes the switch connected to an electrical match that ignites the rocket motor. The design process began in Open Rocket, where I evaluated aerodynamic characteristics such as center of pressure, center of gravity, and overall flight stability to determine an optimal configuration. After establishing the aerodynamic layout, I designed the entire mechanical assembly in Fusion 360 while accounting for manufacturability with consumer-grade 3D printing. Most structural components are printed in PLA and assembled using threaded heated inserts, machine screws, and custom torsion springs formed from piano wire. Multiple design iterations were produced and tested throughout development, allowing the mechanism, particularly the folding fin system, to be refined until it operated consistently and reliably. The launcher assembly is controlled by an ESP32 microcontroller and contains several sensors used for system monitoring and feature development. These include a QMC5883L compass for heading information, a Neo6M GPS module for global positioning, a BMP180 barometric sensor for altitude estimation, and status indicators such as LEDs, and a buzzer for debugging and system feedback. Communication between the launcher and the rocket is handled through an umbilical cord connections that carries TX and RX serial lines. Inside the rocket itself is another ESP32 microcontroller, paired with an MPU6050 inertial measurement unit that provides orientation and angular velocity data during flight. The control surfaces are stabilized using a proportional derivative control loop that adjusts the canards based on measured orientation changes. In addition, the system architecture supports global positioning through the GPS, compass, and barometric sensors, which allow future integration with external tracking systems that require real-time XYZ position in a 3D environment. The propulsion system uses a solid rocket motor made from a mixture of potassium nitrate and sugar in a 65:35 ratio. The propellant is melted and cast into a PVC casing to form the motor grain. The nozzle was designed and 3D printed, then epoxied into the motor assembly. Several static burn tests were performed to evaluate ignition reliability and thrust characteristics before integrating the motor with the rocket airframe. Modern tools, additive manufacturing, consumer electronics, and rapid prototyping have shattered the old barriers that once confined advanced hardware to well-funded laboratories. This prototype explores what happens when these tools are pushed into defense, creating systems that are powerful, modular, and scalable in ways that were once impossible. As the cost of precision continues to collapse, capabilities once reserved for powerful institutions are beginning to diffuse outward, reshaping who has access to advanced technology and who can defend themselves.